Let's talk more about inverted graphing. A little while ago, I made a small video about a concept I called inverted graphing. I was simply curious as to what happens if you try to plot something like this on the Cartesian plane. The results were somewhat interesting. I realized that you can use the indeterminate form of dividing by zero to generate graphs that fill the whole region except for a certain line. But let me not get too ahead of myself. Let's first classify what we actually mean by graphing. Named after René Descartes, who published this idea in 1637, the Cartesian coordinate system consists of horizontal x-axes and the perpendicular y-axis. The brilliance of this is that it allows algebraic equations to be plotted and analyzed on a plane. So for example, let's take this little creature out of the basket. Here we can see that we have two different variables, so we will have a range of different answers for each one of them. For example, if we choose x to be 2, we get this thing, and we can see that y results in 10. We can then graph this on the Cartesian plane like so. We measure out 2 for the x-axis, and then we go up all the way to 10 for the y-axis. And we get this point over here at x equals 2 and y equals 10. Let's now say we choose x to be 1. This will make y also equal to 1. And we can plot it over here like so. We can do this for fractions like a half, making y equal to negative 0.125. And if we make x into negative 1, y becomes 1 one more time. So the idea is that this can be done for any value of x. And if we could actually do it for every single one of those values, which is kind of physically impossible, we would end up with this interesting smooth curve like so. What this does is it gives us a convenient visual representation of this equation here. And of course, this in theory can be done with any kind of algebraic expression, function, or equation, allowing us to analyze them using geometry and vice versa. Now I know this isn't anything new for most of you, but I wanted to just lay out the background of the Cartesian coordinate system so we can clearly explore the inverted graphing method. To do this, we begin with this simple equation. X times y is equal to x times y. Now I know what you might think. So what? Of course xy is equal to xy. There's nothing complicated about this. Absolutely, but I want to start with the most basic of concepts. So let's imagine that we are crazy, and just like before, we try and graph this thing, just for the sake of trying. If we say that x is equal to 1, well, y could be 1, or it could be 2, or 3, or negative 7. In fact, we can see very quickly that you can have any value of x with any value of y for this identity to be true. Which means if we were to actually graph this on the Cartesian plane, we would have to fill every single dot on that plane. So yeah, one giant dark infinite vastness of values. But let's now do something slightly curious. Let's move the y variable over here. Now, at first sight, one might be tempted to say, so what? This and this are basically the same thing. Whatever value you plug for x, you can still plug any other value you want for y. That is until we decide to make y equal to 0, which would mean that x has to result in the infamous 0 over 0. And well, this becomes kind of hard to plot on the Cartesian plane. I mean, maybe if we go past some crazy infinity at some point, we might find the location 0 over 0 on the x-axis, but I really doubt that this is how that works. Furthermore, whatever value we originally assigned for x, we still are forced to give that value to 0 over 0. Which, as you can see, is problematic. The only thing we can say for sure is that we can't plot these values. Hence, this would generate our original filled infinite plane, with the exception of a line along the x-axis, which we are forced to leave empty. All values of x become undefined at y equals 0. I found this concept rather fascinating. A similar thing would happen if we put x in the denominator, except that now our empty line becomes vertical along the y-axis. And to make things even more interesting, when we manage to have both variables in the denominator, we end up with this crosshair shape. We can of course go further with this concept. We can move this shape by modifying the variables, by adding or subtracting some constant to them. If we, for example, were to subtract 1 from y, we force our line to go up by 1 point. And the same goes for x. We can put our crosshair anywhere we want using this method. The more I played around with this idea, the more interesting it became. I wondered if anyone else tried this before, but I couldn't find anything about this particular bit of math on the internet. I just assumed that nobody bothered to graph stuff like x equals xy over y. After all, why would you? And when I tried to plug these into Desmos, nothing came up, so I figured it either wasn't a thing or I was onto something entirely new. Now, the idea of having to encounter something new in mathematics feels amazing. But you know, that kind of thing can be self-misleading. Nevertheless, no reason to give up. Things do get interesting when you try to plug a function instead of that constant. When we shove this equation into Desmos, we get this crazy thing. Clearly, this math engine isn't equipped to handle the finesse of inverted graphing. But we can see it is trying to graph something that resembles a parabola. When we switch our function to 1 over x, we get this. Desmos is trying to generate something that hints at a rectangular hyperbola. And when we plug in our original polynomial, we can sort of see the general shape of that function as well. What we should actually be seeing is a fully filled graph, with the exception of the function itself. This is so because when y is equal to the result of our function, that particular value of x, our denominator and numerator become 0. This forces that original empty line of undefined points to take the shape of whatever function we choose as the difference of y. And this is the general idea behind what I decided to call inverted graphing. I managed to go a little deeper with this concept. Like I said, I wasn't sure if I thought of something new or just a dumb new way to graph functions we already know. But there's a fascinating element to this type of graphing. We can see it when we use the function 1 over x. When we try to plug that into our inverted graph, we, of course, would get the two familiar curves of a triangular hyperbola. The distinction happens when we reach the vertical asymptote, when x is equal to 0. Here we can see that both these terms result in 1 over 0. Now we could say, so what? These cancel out so we can just plug whatever we want for y. But we're dealing with dividing by 0 after all. The other way to view this is to treat this like infinity. But this gives us infinity over infinity, which is even more crazy. My conjecture is that this situation forces us to also leave a blank line at the vertical asymptote, giving us this illustration. I think this is kind of curious, but again, nothing spectacular. My next observation was to note that I can have more than one function in the same equation. I did this by multiplying our original bottom and top y minus functions with another pair of y minus functions. So you see, every time this result would be 0, the whole thing would be undefined, giving us the empty curves of the two functions, which means we superimpose both functions on the same equation, which is something I thought couldn't be done using regular graphing. I always thought that to have two or more functions on a Cartesian plane, you actually need two separate equations. Shows you just how stupid I am. I began to think that I invented some crazy new math with this inverted graphing business. But it turns out that you can combine functions using regular graphing, and it is not that hard. You can, for example, plug in your regular parabola, like so. You can make an adjusted parabola that looks like this. And yeah, both together look like this on the Cartesian plane, and require two separate equations. Or you can plug both functions into this other slightly crazier equation, resulting in this thing, which obviously looks like the original two functions put together, but this time as a single equation. And the only reason I know this is because I thought I was doing something unique with this inverted graphing crap. So yeah, I didn't actually discover anything new after all. Now, I did go to an even deeper level of this rabbit hole. Realizing that I can join different functions together using multiplication, I started to wonder how far I can take that concept. Say we have this classic parabola and this other parabola shifted to the right. To do this, we adjusted our original x value by subtracting 1 from it. And we can combine these parabolas into one equation. Having done so, we can also have another one in between that is adjusted by half. We can have even more by using quarters, or even more by using eighths. And of course, we can do this indefinitely. This reminded me of something familiar, the old product notation. The terms we multiply are very similar and change incrementally. The formula I came up with is this thing. And guess what? Desmos can actually pull it off. The higher the top index is, and also this denominator over here, the more dense the space between the two parabolas gets. And in theory, if this becomes infinity, or reaches some infinite limit, we get a solid parabola-shaped ribbon like so. The same can be done for other kinds of functions and transformations. Here, the parabola moves up. Here, it spreads out. This one fills a diamond shape. And this one fills a circle. I particularly like this one. Now, I thought this could be quite interesting because this process kind of reminds me of integration. After all, we are generating an infinite amount of lines that eventually make a solid shape, which would make this equation somehow related to the area of this circle. But that is something for another video and another time, if it even is something I can somehow figure out. Well, for now, that's that for inverted graphing. This video is already long enough. And if any of you think inverted graphing can actually go in any significant direction, I'm super curious to hear about it. I myself am, after all, just an amateur math nerd and can always use the input of real mathematicians. Well, I hope you guys enjoyed this video. You know what to do if you liked it and want me to do more. And I hope to see you all in the next one. Thanks for watching.